Hello, I'm Joel Chatfield, and this is my Physics Lab 2 presentation. So here's the overview, all the topics we're going to hit. Next, we're going to intro. The intro, we have the system here. It consists of a falling object, which is a Tupperware lid in my case, the floor, which is going to stop the acceleration, the hand that releases the object, and then also will be the air the object is moving through, which is what's going to create that drag force. So here's the initial formulas. You have the standard velocity and position formula, as well as force due to gravity, with g being 9.8 squared. And last but not least, you have the drag formula, which is a constant b times your velocity squared. So here's a diagram denoting how drag works. So weight will be always going down towards gravity, and drag is a force going back up. And drag will almost always be smaller than weight until the object is moving at what's called terminal velocity, in which case b times said velocity squared will be equal to the force of gravity down, meaning it's no longer accelerating. Of course, we're assuming here the drag is proportional to the square of velocity, and that gravity is a constant 9.81 meters per second in the negative direction. So here we have the video of me dropping the plate. See it falls very fast, but not as quickly as a ball would because it has a decently high drag coefficient. So now we have creating the computational model. As you can see, similar to the last lab, we transferred over VF, RF, and regular F over. Regular F is negative here because we've decided that the axis is such that going down is the negative y direction. And then, of course, the drag equation is such that you can't multiply a vector by himself, so we multiply the two magnitudes of the vector by themselves together, and then multiply that by the directional vector of 0, 1, 0. And then the total force is just the weight going down plus the drag going up. And then here is the number computational model. Delta t is 1/3 because it's filmed at 30 frames per second. The gravity is constant 9.81. The only real difference between these two is B on the left is the model with drag, so B has a value. On the right is the model without drag, so B is 0, leading to no drag and no air resistance. And then here's the total computational model. As you can see highlighted, we have drag in there no matter what, but if B is 0, then drag is effectively non-existent in the model. Here are the two computational models. As you can see, the model with no drag continues to accelerate more and more as it goes down because it's no drag. It's going to get faster and faster. And as such, it ends at a theoretical much lower point than either the drag model or the real model, where air resistance is very present because it is a wide and relatively lightweight object, meaning that it fights through drag a lot less effectively. There's a slight difference between the drag model and the tracker model, which could be down to human error. It could also be that we only approximate B, and we don't have the actual guaranteed drag coefficient of the item. Last one is the what if. Which models predicted a terminal velocity? Tracker and the drag model were closer to predicting a terminal velocity. As you can see, they almost flatten out as they go down. The slope almost flattens out. It almost becomes a line, meaning that it almost hits terminal velocity. Because that's when you know when something hits terminal velocity, when it starts when it starts going down at a constant pace, meaning the acceleration has hit 0. And the no drag model is a poor approximation. It can't hit terminal velocity with no drag. It will just continue accelerating. And if an object was initially thrown downwards, it would depend on what the terminal velocity of the object is. If you throw something down with more force than was required to hit make it accelerate to a higher velocity than its terminal velocity, it'll slow down to hit the terminal velocity. Think if you threw a uncrumpled piece of paper, it'll accelerate fast out of your hand for a sec before drag makes it return terminal velocity and it drifts slowly. And if you throw an object like a lacrosse ball, where the amount of force you can impart on it still doesn't make it hit terminal velocity, it'll just approach the ground faster, and if it has enough room, eventually it'll hit terminal velocity. And your throw will make it hit it faster, But it depends on. So yeah, the only difference is it depends on if your initial throw can make it achieve faster than terminal velocity or equal to terminal velocity. If not, it just makes it get there quicker. This has been my lab. Thank you very much.